Okay. Hello and welcome to the last talk we have for this session of Physics Without Frontiers. Today we have Vincent Elfving. Thank you very much. We appreciate your presence and your talk. And I want to introduce you Vincent. He's the co-founder and CTO at Q&Co, a quantum computational software startup based in Europe. His background is in theoretical applied physics, in particular in the areas of quantum information and quantum optics. He graduated with a PhD from the Niels Bohr Institute in Denmark and worked at Google in Santa Barbara as in an experimental team realizing near-term variational quantum algorithms. In 2018, he co-founded Q and Co. together with CEO Benno Broer and is now leading several multi-year collaborative research projects with industrial clients as well as building application-centric quantum computational software solutions. Thank you very much, Vincent. Again, you can start when you want.
Yeah, great. No, thanks a lot for your introduction. I'm very glad to be here and to be able to present on the last day of the session here. So again, so I'm CTO at Q&Co. We've done a lot of interesting research on solving differential equations, which is the origin of what we've been doing here. But today's talk, I want to kind of take you on a journey towards where we believe quantum machine learning and end-to-end differentiability could be applied in a much broader scope than just that. So in this talk, I will introduce very briefly the company and what we're all about, and introduce the quantum solver we came up with. I'll go that's quite high level all, and then I go more into technical details on the DQC algorithm for solving differential equations. I'll also show you a technique that we use to solve stochastic type of differential equations with the purpose of generative modeling, and finalize this with a method for so-called quantum model discovery, or fitting differential equations to real-world observations. So let's get started. So Q&Co is a quantum computational software startup. We started about 3 or 4 years ago. We initially started focusing mostly on chemistry and material simulation. So think about DQE and these kind of things. And from that, we started to be interested also in quantum machine learning for chemistry. And from those research efforts, we started investigating, okay, what else can we do? And we found the target of differential equations to be quite interesting. So we started the second pillar of multiphysics simulations, where we use quantum neural network approaches to solve differential equations that I will detail a little bit more. But on the chemistry side, like I said, we do both this atomistic simulation, so ab initio. We research both the VQE NISQ type algorithms, but also quantum phase estimation or fault-tolerant quantum computing type algorithms, and investigated what would be some typical interesting targets for near-term quantum advantage. And this turned out to be not quite so easy, actually, just like everything in quantum computing. And we found that quite a lot of resources are needed to compete with the state-of-the-art methods in classical quantum chemistry. Other areas where we are currently active is in doing quantum machine learning, or enhancing established classical machine learning with quantum computing. And that's also ongoing projects with clients at the moment. But to complement this, we also started doing these multiphysics simulations. And these, when we say multiphysics, we really mean any situation where there is complex systems, dynamical systems, either natural or man-made, that are governed by sets of coupled nonlinear differential equations in the most general sense. And in this talk, I'd like to showcase how end-to-end differentiability of quantum computing, which is something that we've talked about this week in the context of chemistry, for example, also. But in this context, I'd like to show you that this allows for many possibilities, including modeling differential equations and solving them, but also optimizing design with respect to the parameters of the system, and not just solving deterministic differential equation, but also doing generative modeling, so generating samples from stochastic distributions governed by these models. And finally, I'd like to end up with the learning such models based on real world data, and I'd like to take you through all of those. So at a very high level, we know that many industry relevant problems can be modeled by these different equations. And why is that actually? So in essence, the differential equation describe always some kind of a rate of change and also some type of conservation law. So it's describing physics or rules about the system in terms of rates. Um, think about, for example, Navier-Stokes describing conservation of momentum and volume, pressure, and these kind of things. And sometimes these equations are easy to solve, and you can do it with a piece of paper. But very, very often you have to do it numerically. There are no analytical solutions, and for those, there are many different kinds of numerical methods. If you think about solving systems of interacting molecules where you have billions of particles or more, you would use microscopic methods like molecular dynamics of Newtonian physics interacting between small particles, for example. But if you look at more like fluid dynamics, typically you look at the macroscopic approach where you would discretize your volume into some grid or mesh-based method in real space, or in conjugate space with spectral methods, for example. So you would decompose solutions into Fourier series, Chebyshev series, etc. But typically, these finite element methods, these grid-based methods, are the most popular. But and that's because they are very applicable to many different kinds of systems. So it's very clear cut the procedure how to solve systems with finite element methods. But in the end, they scale quite poorly for more complex problems. So while these are very tractable even on the normal classical computers for smaller systems, if you look at complex systems like nuclear fuel assembly cell or aerospace modeling, for example, this is really intractable to do at the accuracy level that's needed to make a transformational step change in the design and quality of such components in the industry. And it's expected that even Moore's law will not help us here, and that's why alternative methods are being considered. And also classically, alternative methods are starting to come up, and part of these are these machine learning methods, these classical neural network solvers that have gained attention both in academia but also by industrial players like Airbus, for example. So Q&Co has participated in several quantum computing challenges, and we also noticed that this algorithm that we developed has a lot of strong parallels with their vision of how these equations can be solved with machine learning. So, and that's not very strange because the very high level description of our algorithm is that we replace the neural networks that are present in these classical machine learning methods for solving differential equations with quantum neural network approach. So in this case, these physics-informed neural network approaches that have emerged in the past 4 years or so have strong parallels with the DQC method in solving differential equations given some boundary conditions. And the idea is always the same. We wish to represent each component of the differential equation, so the function, but also its derivatives, as being the output of some parametrizable black box, really. So it can be a classical neural network, it can be a quantum neural network. And in either case, we want to also use automatic differentiation or quantum circuit differentiation to get very high accuracy derivative estimates. That means that we differentiate the function with respect to the feature map, so the feature that is the input to the quantum neural network, which is the novel approach compared to existing methods. And in this way, we would variationally optimize a solution. So I'll go a little bit more detail on that because that's a bit too quick. But what is the background of all of this? So the classical approaches typically can be divided into deterministic and variational approaches. And recently, quantum solvers for PDEs have also been developed, and mostly these have been focusing on improving these finite element methods to be faster. And this intuition comes from the fact that you could, in principle, linearize any system of differential equation into a large list of coupled differential equation for each finite element. And together you would be able to access to a 2 to the n sized space within an HHL quantum subroutine, which is known to have a deterministic speedup. So we know that it has advantage over classical, but it has certain drawbacks, of course. It has to run on fault tolerant quantum computers, most likely. It has encoding in amplitudes, which poses this input-output problem that is prevalent in quantum machine learning. And we have to linearize the problem, and we use finite differencing for derivative estimates. So it's not perfect, but luckily there is at least some speed up provable. So variational classical solvers are relatively recent, like I mentioned, but they have various salient properties. For example, they can be much more flexible than finite element methods. There are many things you can do to improve the quality beyond just more points, let's say. And they can also deal with a high degree of nonlinearity and handle sharp gradients. And the only real drawback so far that was noticed in these physics-informed neural networks is that they do require a large number of basis functions and are expensive to train, like many classical machine learning models. So there was a variational quantum solver before for PDEs, which is relatively NISQ compatible, but still it requires controlled unitary operations, and the circuit coherence requirements we found to be quite unfeasible for near-term hardware. Still, it uses finite differencing and amplitude encoding as well. So we saw that, and we saw, okay, how can we learn from these classical neural network solvers? So we use the neural network approach to represent a function f of x given some input x. And we check whether that output, that trial function, that candidate function for a differential equation fits the equation. So is the equation holding for that function? And is the boundary condition holding for the given function? And if not, by how much is it wrong? Call that a loss function differentiated with respect to the variational parameters or the weights in your neural net, and update this with gradient descent or other methods, for example. So we can always write any differential equation in the form at the bottom. So it's some function or some operator on the function together with the independent variables, which should be equal to 0. And if it's not equal to 0, so if we moved everything to the left-hand side, then that magnitude squared, for example, can be minimized in order to find an optimal solution. And a very similar approach was done in 2018. This is called quantum circuit learning. There were also many other papers on the same topic where this sort of parallel was made between feed-forward continuous variable neural nets and quantum neural networks, really. So that they can be trained by using the parameter shift rule to do gradient descent on the variational ansatz. In this case, quantum circuit learning was really used to do regression on data sets. So where initially output of your quantum neural network is just some random shape, we can actually fit that red curve you see here to the final teacher data, basically, and come up with really nonlinear shapes. And that nonlinearity, that ability to represent even nonlinear function, is important for us to be able to solve general nonlinear differential equations as well. So the innovation that we did on top of that is that we represent this function as an output here, but we also need to represent the derivatives of the function. And we could use finite differencing, but this is actually not very practical on these devices because finite differencing for derivative estimates will yield huge errors because of the small finite differencing, right? So instead, what we do is we use these differentiable quantum circuit that consists of two parts, the quantum feature map circuit and the variational quantum circuit. There are many variations of this. You can put many different feature maps. You can put in different orders. You can use data re-uploading techniques and whatever. But this is just a very basic representation of the QNN that we consider. And the output of the function is in essence mapped as a observable measurement on a cost operator of our choice. And we know that such an expression can be differentiated either with respect to the variational parameters, but also with respect to these circuit parameters, which represent the input to the function. So at one point xi, we have some input that we plug in here, and we will get some function output fxi. And we can differentiate this with respect to the input parameter x by, for example, the parameter shift rule. There are also other rules that we can use, but this one in particular is kind of NISQ friendly. So that means that we repeat circuit execution of the same architecture, but with slightly different angles. where each time we use the shifted angles here, as you are already familiar with. So how can we then produce this highly rich representation? So we measure the function by Hamiltonian averaging. So we don't use amplitude encoding. Instead, we say that the function is mapped by measuring an unobservable, and we can choose that cost function. We just have to make sure that each x maps to some unique f of x by the rich feature map. And therefore, it's good to choose your cost function in a certain way. For example, to avoid barren plateaus. For example, to have enough richness in your spectrum, but also in order to make it feasible to do on a real device, we preferably choose a cost function that is only diagonal in its operators, right? Otherwise, we'd have to repeat the measurement for all the non-commuting parts. So we can not only choose a smart cost function, we can also tune the parameters in front of each part. So that means that the output in all its glory and all its detail can also be the input to a classical neural network, right? So how do we then quantify the quality of the solution? So we use a loss function for that. So we say, what is the distance between left and right hand side for a differential equation averaged over many points in the domain of interest, and look at the squared or the absolute value difference, for example, of the differential equation itself. That's what we call the interior loss, but also whether it matches the boundary condition. So what's the square distance, for example, between the differential equations initial condition and boundary condition, respectively. And this loss function description is really flexible. So we can add whatever we want to that. We can add regularization terms. We can add many different kinds of things to that. But the schematic overview of the full algorithm. So here you can see on the right-hand side a typical evolution of solving a very simple differential equation here, df dx equals x or something like that, with f0 being 1. And how does this actually evolve to become better and better? We see that the loss goes down like this. And in general, we can choose many settings. So we have as input the differential equations, the boundary conditions. We can choose many aspects to the DQC. That means we can choose the feature map to be either a product map, Chebyshev map, tower map. So there's many settings. We can choose the loss function, the boundary handling, pin floating. We can choose many different cost function and variational Ansätze. Then we optimize the circuits by saying that, okay, let's look at a grid on the domain of interest and test whether the function fits the equations at each of the points in that grid. And this grid can be actually relatively small compared to the grids you're familiar with from finite element methods. So these are not huge grids. These are only as big as are required for capturing the main characteristics of the solution. So that means that you need to be able to capture the dynamics of the system within the spacing of this grid, which can be done with very few points. So we evaluate at every point the function, the derivatives, and also the gradients of those components with respect to the variational parameters that are inside the circuit, in order to do gradient descent using classical optimizer, or conversely, we can use some gradient-free methods, right? And finally, what is the solution actually? So the solution is a set of angles theta that determines the shape of the output f of x of your quantum neural network, which can finally be evaluated at every point in between, not just the points where it's trained at, but also interpolated between that. So that means that in that sense, it's a machine learning approach where we're training on a limited set and evaluating or testing on a set outside of that. But in principle, the interesting part here is that we don't have actually any training data per se that it's trained on observations. It's purely trained on physics. It's trained on the model itself. And that means that we restrict the possible functions to be exactly those which conform to the physics that we prescribe. And that's very fancy words for saying solving the differential equation. Then you can also add your own data, etc. But that's what we'll do in the next phase. So a very brief example then of using DQC to solve a quasi-1D Navier-Stokes type problem. So we have this convergent-divergent nozzle situation going on where we're basically putting some fluid that's going less than the speed of sound initially, but we're starting to press it through this really narrow region here at x equals half. And we expect that under some conditions, this actually results in a supersonic flow going out. These are the kind of situations that are very rough models of what happens in aerospace industry, for example. And when we choose certain parameters, we find that there are certain situations which are actually quite tough to solve even classically and numerically. Although, of course, disclaimer, you should be able to solve it on a laptop if you do the right settings. And here we solve this with 6 qubits. So that means that our feature map could resolve with a 6-qubit Chebyshev-like feature map the kind of features that are required to represent such shapes, where we used a little bit regularization between this step and this step to actually conform nicely to the final shape here. And you can see here how the loss in terms of the interior loss, the boundary loss, and the quality with respect to the solution goes down as we go from 0 to 600 epochs here, roughly. So, of course, this being a variational approach, it's very hard to predict how this scales with the problem complexity. But more importantly, it's not clear how problem complexity translates to any kind of quantifiable complexity in general. It's not like solving a model Hamiltonian for its ground state, which is much better understood. There are aspects of stiffness, etc. But what is interesting is that there's a lot of recent research going on in the classical physics informed neural network community that actually showcases the tremendous progress that's being made in these variational approaches, where these quantum machine learning approaches can also lean on. So we can learn from that adjacent track of research that is still very fresh. So the steps and examples that we have just worked through, they show some of the benefits that our algorithm has compared to previous methods. Although, of course, it's a little bit of a marketing picture here. There are some salient features to the approach that include being able to natively handle nonlinearities, to be relatively resistant to noise due to its NISQ friendliness. We don't deal with an input-output problem directly because we're using Hamiltonian averaging and quantum feature maps rather than amplitude encoding. And I also want to highlight the flexibility of the approach. So I've so far only showed you a very simple set of coupled differential equations, but actually this method is a high-level strategy for solving many different kinds of differential equations. So they include higher order ones, very nonlinear ones, discontinuous ones, algebraic, different kind of boundary conditions can be considered. So many different aspects of differential equations can be incorporated, mostly due to the flexibility of the loss function, I would say. And I showed you some spectral decomposition, but nothing stops us from using even finite element-like or discrete grid-based or even mixed feature maps. It doesn't have to be Fourier or Chebyshev. It can be discrete as well. So finally, the outlook that I wanted to show you on this approach is also the stochastic differential equations, which are a little bit different because it is not immediately clear what one means when they say solving a stochastic differential equation compared to these deterministic ones above. So that's what I want to take you through a little bit here. So this is a work that's been done together with Professor Kirienko and our sponsored PhD student Annie Payne at the University of Exeter, at which we also did the research with DQC. And this perspective here, this paper that we released in summer this year, is called Quantum Mechanics. And the goal of this paper was to investigate, okay, what do we mean with solving SDE, and how can we do this with quantum computers efficiently. So our idea here is to take any general, potentially nonlinear set of coupled stochastic differential equation with some drift term f and some diffusion term g. So these can, in general, depend on the stochastic variable xt and time t. And you see here that there is this Wiener process wt here, which is the origin of the stochasticity, whereas the drift here is really the deterministic part of the PDE that's present here. So we have a very general SDE, and we ask ourselves, okay, let's solve it. What does that mean? So one way to do it is to rewrite this equation as an equation for the probability density function, the PDF. And then you actually get a partial differential equation. You could solve that with DQC. But what that would give us is just the evolution of the PDF, the distribution, through time. But it does not allow much practical use, because it does not allow for generating samples from that distribution. Instead, we aim to solve the quantile function, which is the inverse function of the cumulative density function, which is the integral over the PDF. And this quantile function does allow for efficient generation of time series data, and it allows for rewriting the SDE in terms of a deterministic PDE describing this quantile function. So the quantile function is a generator of samples, literally. So it is something that if you plug in a uniformly distributed variable, you get out a sample according to the distribution of the underlying distribution. And that means that you can save a lot of computational resources, because in general it is expensive to sample from a general probability distribution, while it's relatively cheaper to sample from uniform distribution. So we developed this so-called QQM method, and you could put it a little bit next to the idea of the Monte Carlo methods that are very popular for solving SDEs, where in Monte Carlo you would trace out one trajectory of a realization of x of t with some random number generators for the Wiener process, and you would repeat, you would sample many times, and at the end you would get out some probability density function, and you would get some mean and some variance, and that's really interesting, and you would in principle get samples, but it would quickly run into the curse of dimensionality as you go to a higher dimension of your stochastic variable. So the other idea would be, like I said, to solve with the DQC method the Fokker-Planck equation for the probability density function. And this is in principle feasible, and it would allow us to compute the mean and the variance as a function of time and other potentially higher order observables on distribution. But it would not give us direct access to the samples. And for that, we do this quantile mechanics method. And it's important to note that the quantile mechanics method it's already a few years old, but so far this method of solving it was only done by solving the PDE that comes from Fokker-Planck, to actually solve that with the power series methods or other a little bit older techniques than these novel physics informed neural network techniques and DQC techniques. So that's the novelty in this research here. And the application of generating time series is in, for example, market prediction, but also in generating data that needs to be anonymized. So let's say you have a data set, but it's coupled to real world clients or customers in the EU, for example, where there's very strict laws on like GDPR for customer privacy. But you still want to have train a machine learning model on such distribution underlying the data. So that means we cannot just copy the distribution. We have to learn a distribution and then sample from it. So what you could do with this method is you could generate synthetic data based on the same underlying distribution of a regular real-world data, in effect anonymizing it, basically. And importantly, seeing the development of this through time. So that's the other novelty in this approach, is that we're not just learning distributions that are static, but those that are evolving or dynamic in time. So the summary of this overall strategy is we have an input stochastic differential equation dominated or described by the drift and diffusion terms f and g, and we're given some initial boundary conditions. And importantly, these can be analytical, but they can also be data. So we can train the quantile function, that's the output of our quantum neural network, to fit either an exact description of reality or actually try to fit the limited representation given by a data set. But in either case, we train it to fit that at a certain time point t equals 0. And then we train also time larger than 0 according to the prescribed quantized Fokker-Planck equation with the method called quantum mechanics. And the optimal angle is found. And given such optimal angle, we have a setting of the quantum neural network with these two feature maps, one for the latent variable z, one for the time component t, to generate samples across this quantile function that is now a function of time. That means we can generate time series. We can generate samples at different points in time according to, for example, the histogram that is evolving from initially being there to being a bit broader and moving its mean, for example, here. So as a first test case to exemplify how this works exactly and what you can do with it, we target this very basic model, this Ornstein-Uhlenbeck process, which originally was really used to model the velocity of a Brownian motion particle under the influence of friction. But it just has a linear diffusion term. It has a constant drift. So it's the most simple SDE you can imagine, really. But it has some nice properties that it has, for example, an analytical solution. So we can easily compare whether our method works. And it has an intuitive behavior. It's basically mean reverting. So there is some, wherever you start, it will always go to the same mean, and it will decrease its variance. So it's a kind of random walk in continuous time. You can see it. But for all its simplicity, it's actually used, when you modify it a little bit, it's used to model interest rates, currency exchange rates, and commodity prices. So it's actually known in trading strategy also as pairs trade method. So it's quite interesting. We compare it also with analytical and numerical Euler-Maruyama methods, and we find that we can propagate our quantile function in time, starting from a minimum time where the quantile function looks like this for a Gaussian initial distribution. And we see that the quantile function changes shape and transform as we go to the maximum time. And the more familiar picture for the human brain is, of course, the probability density function and its corresponding histogram that you would see that follows this distribution. And you can see that the mean is basically moving this way, and the variance or the standard deviation is expanding in this case. And we show that well, there's many different ways to quantify differences in distributions. We chose here to just do difference in counts between these distributions, and we find a very close resemblance here. So future research would include doing this in higher dimensions to see if we can do properly completely non-Gaussian looking distributions and other things as well. So finally, the last thing I wanted to talk about is this quantum model discovery, which is really quite recent paper we did together with Niklas Heim here from Czech Technical University, and together with Sasha as well from the University of Exeter. So we call this quantum model discovery. So not quantum model discovery, but model discovery with quantum computing, where the idea is that, first of all, we would be able to learn the parameters of a differential equation. That's the basic setting. Let's say, for example, we have a damped harmonic oscillator. So we have just some mass attached to a spring, and it's experiencing damping, so friction. And we have some observations of this experiment, let's say some data points, right? And our aim is then to predict the data in between and also in the future, and also the physics underlying it, given that we only have estimates of the differential equation. So we only know that omega is some number and alpha is some number, but it's actually not very accurately known. We just know that these terms exist. then what we can do with quantum model discovery is we can put all of this in a regressor and fit not only the data, so the output of our quantum neural network, but also the terms appearing in the differential equation. And you can see that this actually works quite well in very few iterations. And that gives additional benefits, because it no longer means that we need to know a perfect differential equation and solve that perfectly. And even if we do that perfectly, it wouldn't be helpful if we didn't know the right equation in the first place. But instead, we're relying here on real world experimental data, fitting a model to it to understand the material properties, like what is the damping rate or what is the natural oscillation frequency. We can retrieve that by fitting it. And we can actually go one step further. So far, we assume that we know the terms of this differential equation, right? Well, with model discovery, we really try to even learn what the equation looks like at all. So we would assign some weight in front of every term in a differential equation. That can be either the function itself, its derivatives, or any other thing, really, where each term is measured as the output of a differentiable quantum circuit. So that can be either the function itself or its derivatives with respect to the input. And given that it has to fit the data and some model, we force the loss function actually to shape the coefficients in front of each of these terms such that there's only one real option. And we also enforce sparsity. So that means that we might end up only with a few terms in the differential equation being correct. And to give an example here, let's say we don't know anything about the equation except that there is some second order derivative with respect to time, and we try to see whether we can fit linear or higher order terms or derivatives, and then what not only what the size of the coefficient is, but even if the coefficient is there at all, or in other words, that the coefficient is zero. So you can actually go to a surprisingly large library of such functions and still be able to fit the output of a quantum neural network in a fully differentiable approach, um, essentially learning the equational form, learning the physics, really. So this is a method that is known only recently also in the classical machine learning method literature, called deep model discovery. And we essentially used the DQC method to modify some parts of this in order to represent functions with a higher, larger dimensional feature space. That's a real novelty there. Yeah, and we were quite excited to see this as quite the first step towards something that we'd like to call quantum scientific machine learning. So, like I said in the beginning of my talk, the end-to-end differentiability of quantum computing algorithms allows for many different possibilities. We've seen this in chemistry already, but modeling systems by differential equations and solving them, we think, is a really natural fit. It's an example where end-to-end differentiability can really be beneficial. So that means not just for solving known deterministic equations, so PDEs that we know exactly the right numbers for, but also learning these models based on real-world data. And one thing that I haven't mentioned yet in this talk that I also personally find quite interesting is that the feature maps that we use are typically features that are real-world dimensional positional data, right? The XYZ or time, something like that. But we can also make other properties of the system as being an input to the quantum neural network. We can choose the width, for example, of this convergent-divergent nozzle to be a input to the neural network. And what does that mean? That means that we essentially are training sparsely, so across a few example points of the width selection, so width being 5, 6, 7, 8, and training at those points, we would gain an understanding of what the solution would look like also in between. And this would allow us to do design of components using end-to-end differentiability. And I think that's also a very interesting aspect. Then finally, the solving stochastic differential equation for generative modeling is an approach that I think is also just the first step. We don't know exactly where is the advantage potential coming in there. We believe we have to do a little bit more research to really figure out how to make this even more efficient, either combining it with known methods in generative adversarial networks, for example, or in QCBMs. But we hope that such methods inspire people to also figure things out with these kind of techniques. So with that, I'd like to finish this talk for today, and thank you for your interest. And also, there is the shameless plug here to say that we're hiring both postdocs and PhD, so you can contact us here. Thanks.
Thank you very much, Vincent.
Yeah.
That was a great talk. I think we have many questions here, and I have a list of them here. Thank you, Suar. First, what will be the effect of noise in the performance of the algorithm?
Yeah, that's a great question. So what would be the effect of noise in the algorithm, right? So there are different kinds of noise, but I assume here that one would talk about the noise of the quantum computer itself. So meaning that when you measure the observable coming from the projecting the operator on the quantum state at the output, there are known, several known sources of noise here. So that means we take a finite number of shots, for example. So the evaluation of the function at this cost operator here would require you to take a number of shots that is enough to estimate this cost function with a certain precision. And really what it comes down to is how large is the spectrum of this cost operator as compared to the range of your function in the domain of interest, and as compared to the precision that you require within that domain. And what we find in practice, depending very much on the application, of course, is that if the range of the cost function goes from here until here in this map, then even 5% error across the entire spectrum is fine for so-called solving this differential equation. It's not that it's as sensitive as, let's say, VQE, where we want to have chemical accuracy, which on the grand scheme of things means we want an extremely tiny energy error with respect to the spectrum of the Hamiltonian of interest, right? So it's looking at these percentages that you can see that the noise requirements for this to work are actually quite a bit lower. That's from a theoretical perspective. From our practical experience, we have tested this also on real-world computers, even with very little optimization. So just sending it to a publicly available IBM quantum computer, for example, we actually got very nice results, at least at 2 qubits. We are also working at investigating the results for larger number of qubits, but that's still work ongoing. Yeah.
Okay, thank you. A second question. As you showed, the QQM method will be used to predict market. Could this method be used to predict the price of cryptocurrencies in the future, or maybe complex pandemic models?
Those are interesting application areas. So the question is if it could be used to predict the price of cryptocurrencies and or something about pandemic. Oh, sorry, what did you say?
Yes, pandemic models, complex
pandemic models. Yeah, so some stochastic properties of how
the simplest
infected
pandemic
diseases
models
are spreading.
are sets of differential equations.
Yeah. No, I think that might be the case. What we're currently figuring out is there are different, like I said, there are different aspects to solving a stochastic differential equation. Very often we might have the goal is to find a solution to a PDE that's a little bit stochastic, right? That's not the focus of this particular research. I think that the DQC method would work there still, but the setting here is more about generating samples from a distribution that evolves through time, and the use in that is maybe not so much centered around price determination directly, but rather in supplying data that other machine learning can then access, for example. So think about that in the case of cryptocurrency, right? So we might have a very new cryptocurrency and we only have data of its price over the past 3 months, not just several decades like other financial markets. And with this very limited amount of data, many machine learning methods can actually not directly learn trends or make price predictions because of the limited data. So what we could do with these generative models is to generate data that follows this distribution by learning it, not based on just the data, but also some theoretical models that are known in economic literature, and together generate more data according to that distribution that would then be useful to training other machine learning models. But yeah, certainly very interesting suggestions, and I'd be happy to think about that a little bit more.
Okay. Then we have another question. What was the smallest error found comparing the QQM and the Euler-Maruyama methods?
Yeah, great question. So I think that the very difficult part about estimating distribution differences is that in principle, in order to make sure that there are no errors or differences between distributions, one would need to go to the limit where you compare infinitely many samples from the one distribution and infinitely many samples from the other distribution, in principle, if you just have data. Now, there might be methods in which you could compare directly the output of the quantile function with the Euler-Maruyama method, but I'm not so sure how easy that would be. So to answer the question, we don't know necessarily whether these count differences stem from the finite sampling we do, or whether it's slight differences in the exact and trained quantile function at this end, at the tail end that you can see here. It might be one or the other that is dominant. It's hard to tell. Yeah.
Okay, we have another one. If you can start with an ansatz, if the ansatz is close to a local minimum,
Yeah.
can the method find a global minimum of the loss function instead of being stuck in that local minimum?
Yeah, that's a good question, right? And I think that's true for quantum machine learning, like for anything, for any variational ansatz, really. And I think that for the whole community, for all of the methods that are related to such problems, it's important to think about the balance of expressivity and trainability, and make sure that we can somehow have enough expressivity over parametrize, make sure that we're in the regime where we're guaranteed to get good convergence. And that's certainly not a trivial theoretical effort either. There are many great recent efforts on this topic. And we're currently working on seeing how these results extend to the types of loss functions that we have. Because in the end, it's kind of interesting to see, let's see if I have like the loss function here, right? It consists of contributions of f of x at different xi. That means that there are contributions of cost function evaluations at different points. And that's a slightly different setting than saying your loss function is simply a cost function, really like a Hamiltonian minimization problem, because then you're talking about properties of ground state. And here we're really looking at a loss function being the square root of the sum of things that are somewhere in the excited state space. So we don't actually know properly, it's not well understood what the properties of such loss functions are with respect to overparameterization, etc. I think there's a lot of research to be done about making sure that if you indeed start at a local minimum, then, and that can always happen, that you can somehow ensure that that local minimum is satisfactory, that there are many that you like, that it's okay that you get stuck there. That's really to hope for that. Yeah.
Okay. We have another one. This can model discovery be used with nonlinear differential equations?
Yes, certainly, and we advocate to do so, and that's because I think that typically for classical computers, linear equations are just sufficiently solvable by classical numerical methods in many cases. It's really nonlinear equations that are hard. And I showed here a linear example, but nothing prevents us from putting much more complicated things. So in this library, you can see some quasi-linear term appearing. We tested it for other terms as well. You can actually see the nonlinear terms appearing in the library here. Now, of course, the ground truth happened to be linear, but we can also make the ground truth nonlinear, and it would still work. And the reason for this flexibility, for this nonlinearity being compatible, is really because we only have to represent u of t in this case in order to compute u to the third of t, because we evaluate it as being a function output that we can take the power of, right? So the operator to the power 3 is a differentiable operator, and that doesn't hamper us in our end-to-end differentiability. So in that sense, we can come up with any kind of nonlinearity and it would still be compatible. How well it works always depends on case by case. Yeah.
Okay, and yes, we have time. Marco added a question here. What quantum feature maps have worked for you? Sorry.
Yeah, great question. So I have some extra slides for this. We find that Chebyshev type quantum feature map works for our use case very often because, there are many different feature maps that exist, and some that are very popular include Fourier feature maps, right? Chebyshev type feature maps, they're quite good in situations where you neither have purely oscillatory solutions nor purely decaying functions, but a combination of the two. So if you look at an example, which is this light yellow oscillation here, that also has a decay as you go away towards the x equals 0, we can actually fit this quite nicely with these Chebyshev type basis functions. And the feature maps that we use, the most basic ones, really look like this, where we do an Ry rotation on every qubit, and we have a nonlinear function called the R cosine of x inside this rotation. And because the Ry naturally projects on the z-axis with a cosine type behavior, you get this kind of cosine of R cosine with a certain frequency inside. You can call either an order or a frequency. That means that the output of such a quantum feature map looks a bit like a combination of a projection of the Chebyshev Chebyshev polynomials of first and second kind on the 0 and 1 state respectively. Then you of course just have a product of n polynomials, which doesn't really help. It's still classical. But then when you start to add variational ansatz, all of these terms are mixing. And due to chaining and nesting properties of Chebyshev polynomials, you actually can reach higher order polynomials, just like in Fourier, right? Because in Fourier series, when you multiply or add different frequencies, different frequency waves, you would also get the sum and difference beating effects of the frequencies. And the similar property holds for Chebyshev type feature map. So in the end, the output wave function is some really non-trivial function of Chebyshev feature maps, Chebyshev polynomials at the end. So that's the feature map we use the most. But we've also ran into situations where Fourier type feature map are good. We have not played so much with discrete feature maps so far, but we'd be happy to try that as well.
Okay, thank you very much, Vincent. It was a great talk we have today.
Mm-hmm.
I would like to thank you again for the time, for the preparation of this talk.
Right.
I think our students enjoy it a lot. And okay, I want to thank Felipe and Subadra and Marco too, because this is a great job they did for today. So
Yeah.
thank you very much. We have your email, and maybe you can hear about some applications for Q&A Co from Guatemala, from people from
Yeah, I hope
this
so
this
too.
course.
Yeah, thank you
Okay,
very much for organizing, inviting, and chairing this session, Giovanni. So thank you.
okay,
Yeah,
thank you.
thank you very much, Vincent. It was a pleasure.
Yeah, great. Hope to see you again, and have a good day. Bye-bye.
Okay, bye.